All right, let's do the second part. Now, technically, this is the question before this one. So we did what was alpha if you cut the string on the far right-hand side of this long, thin rod and it was free to swing down and to the left, which would be clockwise, which would be technically a negative torque, even though alpha was entered, I'm pretty sure, as positive. But the previous question was, let's consider the system before we cut the string. How hard, remember there are three total forces on this meter stick. There is, starting from the right, there's tension from that string that we're going to cut in a minute, holding up the meter stick. There's the weight acting in the center of, acting from the center of mass, so in the middle. And then there's actually the force of the axis. So there's a pin going through the meter stick and into the wall, holding it up. And we're even free to pull that out. That's actually kind of an important point. Because that pin has been designed so that I can pull it out, we actually need to consider what happens if we let the meter stick swing about the string instead of about the axis? What if it was free to rotate down and to the right? So it's kind of a thought experiment in order to find the force on the axle F. Well, that's so second part of the video is let's find the force the axle is pushing up. So in order to do that, we're going to imagine that we can let the thing rotate. We can pull that pin out and let it rotate. So, or more accurately, kind of a better way to describe it is this. If that's true, if it's true that we're considering the force that axle, that the axis, it's hard to consider which word to use. If it's pushing upward, that means the sum of the torques must be zero. There's a torque from the axle, there's a torque from the weight, and the two of them must be balanced. So how is that going to help us solve this problem? Well, we need to consider the two torques. So if the axle, remember now, our axis of rotation is now the far right-hand side. So that point where it's over here attached to the string, that's going to be the point about which it will rotate. So this rod, if there were no pin holding it up on the left, if we could pull that out, then the end of the meter stick would actually want to rotate down and to the right. So that means that the force due to the axis over there on the far left-hand side, that is causing it a torque that would want to rotate in a clockwise way. Okay, let me say that again. Even though nothing's actually moving, the axis on the far left is pushing up. And if we consider the far right-hand side our pivot instead of the far left-hand side, if we think about that, then the force pushing up is causing a torque that would want to make the meter stick rotate in a clockwise way. So that's a negative force, okay? So there's also to consider the weight. What torque is it causing? So looking at the mg acting in the middle, if the axis of rotation were the far right hand side, that would be wanting the meter stick to move in a counterclockwise way. So that means that L in the last problem, the torque L over 2 times mg was negative. Now it's a positive quantity because it wants to make the meter stick rotate in a counterclockwise way. But the force on the end, which is F times L, that's how far. Here, let's pick a different color for that one. Let's do pink. This is the other axis of, or the, you know what? Let's actually erase the, here, I'm going to erase these. I made a mess. Let's draw the two. So we've got this lever arm here, all the way over there, and we've got this lever arm here. They're both from the far right-hand side. Let's go back to black. That's very pink. So the lever arm for the weight is L over 2. The lever arm for the force on the axis pushing up is L. So think about how much more complicated this is as a thought experiment. Now we're saying nothing's actually going to rotate. And again, this is number 2 from the set of UT homework questions for this week, which is technically the first one in the set. And I found in my mind, considering what's going on with alpha when I cut the string, was an easier question than thinking about what we're doing here. So we're having to imagine if the axis were able to make the system move, then the meter stick would rotate up and to the right. If the weight were greater and able to pull down, it would make the meter stick move down and to the right. So it would rotate in two different directions depending on which torque you're thinking about. The torque coming from the axis is in a clockwise direction, so that's a negative one. So that's this one here. The torque from the center of mass, the weight, that's this one here, would make the thing rotate in a counterclockwise way. So that's why they're oppositely directed. Okay, so one is positive, one is negative. So that means the torque from the axle, F times L, equals the torque from the weight. We can set them equal to each other. So you can actually, even though nothing was actually moving, because we were able to apply torque in a potential rotational sense, we were able to answer this question. So that means that the lengths of the uh, meter stick actually cancel out, and we're left with the force from the axis is going to equal mg over 2. Another way of saying that is it looks like it's half the weight, which I hope that makes good sense. Now that we've gone through all of that thought experiment, each of those left and right hand sides, the tension on the right, the axis on the left, each one has to hold up half the weight because each one is half of the length from the weight itself, which means this is a very important point. The center of mass is the how do we put that? Where weight acts. Where the weight acts. So that's a weird but important point. Whenever you're considering a rotational system, what you're really saying is, how is the weight impacting this? And if the weight is distributed correctly, it's going to be in the center of mass. Or more accurately, a better way for me to say that, that sounded a little wishy-washy. The weight always acts from the center of mass. The question is, where is the axis relative to the center of mass? If the axis is at the center of mass, then the weight's not going to cause a torque. But that's not true in this problem. Here, we're either going to consider the axis on the far right-hand side, and in this thought experiment where we could pull the pin free and let it rotate down and to the right, or we're going to cut the string and let it rotate down and to the left. But either way, the weight itself is acting as a torque, and it's half of the distance away. So let me say it again. It's not at all surprising that the tension is holding up half the weight, that the force on the far left-hand side from the axis is holding up half the weight. That's what you would expect. And essentially, we just proved that to be true. Each upward force, each upward pointing force is essentially holding up half of the weight because this is a long, rigid rod that's uniform. So it makes sense that on the left it's holding up half the weight, on the right it's holding up half the weight. We just use torques to prove that as kind of a thought experiment, okay? So there you go. It's always going to be half the weight. The axis is holding up half of the weight. Okay, I hope that's good enough for now. That's 2 of 5.